It's fine. Okay, so good evening, everyone. Thank you for coming at this first webinar. It's a series webinar on quantum sensors. This first one is dedicated on quantum sensors on ground. Then on the following webinars in the rest of the year, we will talk about quantum sensors applications and quantum sensors in space. So I am Célia Pelluet. I'm a quantum sensor engineer here at CNES, and I will be your chairman for this session. So online, can you hear us well? If someone can tell, it would be great. It's fine? Okay, great. First, a little bit of advertisement for the CARIOQA podcast, because so those webinars are dedicated to the scientific public, to the curious public, but also we have a podcast that is more for, let's say, dissemination for a broader audience. So don't hesitate to share it with the people who could be interested and to go see it online. It was recently released. And it's the podcast subjects are linked to the webinar subject. So it's interesting to hear both of them if you want to understand the topic. So first, I will try to explain to you the general context of CARIOQA and also present our speakers. And then we will start with the questions that we prepared and then the questions of the audience. Don't hesitate to ask questions. So, CARIOQA is a space mission funded by European Commission that aims to send the first accelerometer on board a satellite. It stands for Cold Atom Rubidium Interferometer in Orbit for Quantum Accelerometry. PMP stands for the Pathfinder mission preparation of the project. And to present a bit the project, I'm going to share with you a video that I hope is...
Welcome to CARIOQA-PMP. My name is Christine Fallet. I work at CNES, Centre National d'Études Spatiales, the French agency for space research for the last 30 years. I currently coordinate the CARIOQA-PMP project, which stands for Cold Atom Rubidium Interferometer in Orbit for Quantum Accelerometry, Pathfinder mission preparation. Let's discover what CARIOQA-PMP is about.
The project focuses on adapting quantum gravimeters for space use. This groundbreaking technology is currently only employed on Earth for ground evolution studies. This initiative lays the groundwork for a Pathfinder mission to test a quantum accelerometer in orbit, setting the stage for advanced sensors to enhance Earth observation and climate change monitoring. CARIOQA-PMP is a €17 million project funded by the EU's Horizon Europe program over 3 years, involving a consortium of 16 key EU space industry and academic figures from 5 countries. Led by the French and German space agencies, it aims to advance a pioneering quantum pathfinder mission using our collective expertise in quantum technology and space missions. Now, to understand why it is relevant to measure gravity, and to better grasp the interest and stakes of adapting quantum gravimeters to space, let's have a look at some physics notions. According to gravitational laws, the ground mass distribution directly influences the Earth gravitational field. For instance, water doesn't have the same density than dry soil, and consequently the same gravitational attraction. Therefore, the measurement of the gravity is paramount to identify ground specificity that we cannot observe with naked eyes. Quantum sensors are breakthrough technology that will provide more accuracy than past and present space missions. This improvement will contribute to a global and repetitive remote sensing of mass changes in the Earth system, ocean, atmosphere, cryosphere, solid Earth, allowing the monitoring of related essential climate variables and help monitor geodynamics phenomena related to earthquakes, volcanic eruptions, and ice melts. The goal of the CARIOQA mission is to test the ability of a quantum sensor to measure acceleration in microgravity on a dedicated satellite platform. The level of sensitivity and accuracy of the instrument will be determined in orbit by probing the drag force acting on the satellite. The results of this characterization will enable to design and provide ultra-sensitive sensors for future scientific space missions, outperforming classical technologies by orders of magnitude. Let's have a look now at this promising technology, the quantum accelerometer, and how it functions. Rubidium atoms are first prepared from a vapor to form an ultra-cold sample using an atom chip. The atomic cloud is then moved away from the surface of the chip and collimated via magnetic lensing. Then the free-falling rubidium cloud successively interacts 3 times with a unique pair of retro-reflected Raman beams acting on matter waves as beam splitters or mirrors. This creates an interferometer that enables to perform absolute acceleration measurements using the atomic cloud as a test mass. The atomic population in each output port of the interferometer is then measured by 2 cameras using fluorescence and absorption techniques. It enables to determine the output phase shift of the atom interferometer, which is then proportional to the acceleration. In space, we will benefit from the microgravity environment to increase the sensitivity and accuracy levels by orders of magnitude by manipulating the atoms over several seconds. The different components of this quantum accelerometer will be accommodated on the satellite. The atoms will be manipulated inside a physics package placed at the center of mass of the satellite. A laser system will provide the light to cool, interrogate, and detect the atoms. The quantum accelerometer will be surrounded by all the components necessary to operate the satellite. After the launch, the solar array is deployed, and the satellite will reach its orbit to achieve the acceleration measurements. CARIOQA is only the beginning of a long and fascinating journey towards the use of quantum sensors in space. More than a technological milestone, CARIOQA mission paves the way for improved gravity missions following the successful GRACE missions, which provide essential climate variables and thus help us understanding and monitoring climate change.
So I hope you know more about CARIOQA now. Again, the sound on the online, did someone say something? So first I want to thank the speakers, the experts that are going to give their insights on this topic of quantum sensors on the ground. We have first Franck Pereira, who is from the Observatoire de Paris. He's head of the Atom Interferometry and Inertial Sensors group, and he's the co-PI of the CARIOQA space mission. We have Vincent Ménoret, who is from Excel Company. Oh, spoiling. Who is from Excel Company. He's senior scientist, and he's co-leader of the team in charge of quantum gravity sensors and involved in a joint laboratory called X-Atom. And we have Dr. Christian Schubert, who is from the German Aerospace Center of DLR, specifically from Institute for Satellite Geodesy and Inertial Sensing. And so he's head of the Quantum Sensing Department at this DLR Institute. We can give them a round of applause and thank them very much for agreeing to take part in this roundtable. So I have some questions that I will ask to each one of them in order to start this conversation, this panel. So first, I'm going to ask Franck if you can explain to us the science behind quantum sensors.
Okay, I can try. I think the movie did a good job somehow explaining the working principle of the accelerometer. So this is also sketched here with this drawing that you see. What makes this sensor quantum is that it is based on the law of quantum mechanics, and it exploits the fact that atoms behave not only as particles but also as waves. So this is the so-called wave-particle duality of matter. And this is something that allows to actually split the waves to realize this atom interferometer, where laser beams are used to basically create coherent superposition of quantum states that travel along the 2 different paths in the interferometer. And then in the end, we are able to recombine those waves. And as it was explained in the movie, I mean, in the end, we measure a phase, an interferometer phase, which is the difference packets along the 2 paths. And it turns out that for atoms, this phase is proportional to the acceleration along the direction of the laser beam. And very important for this technology is the fact that this phase shift The scale factor, so this relation that one has in between the quantity of interest, which is the acceleration, and the observable and the measurement, which is the phase. In this scale factor enters parameters which we can control and determine very precisely, because you have k, which is related. This is the wave vector of the light, so it's tied to the wavelength of the laser that is used to create the atom interferometer, and big T is the time between two consecutive impulses, and those wavelengths and are frequencies. Frequencies and time are the quantities that we can actually measure with the best possible precision. And this is something key because it gives to this interferometer its enhanced performances, in particular its accuracy, since the scale factor depends on quantities that we can control extremely well. Another thing of interest is that it also provides very stable measurements. So it's a very sensitive device. This phase shift is actually very large for like a displacement of a few centimeters of free-falling atom. You have a phase shift which amounts to like thousands or tens of thousands of radians. And if you're able to measure this phase with a good phase resolution, and we can do in the lab, and maybe we will discuss something like, fraction, a very small fraction of an interfringe, so like, millirad kind of sensitivity. This immediately translates into a relative sensitivity to the acceleration, which is extremely, extremely large. Okay, that's what I would say too.
Yeah, thank you very much. So we can measure accelerations with a very good accuracy. It can be used to measure gravity because gravity is an acceleration. And so this leads to my next question to Vincent, which is, what is the state of the art for gravimeters that are based on this technology on ground currently?
Okay, so again, it's a very broad question. So I've selected a few applications to try and give you a flavor of where the field is headed right now. First, static gravimeters that can measure gravity are now field proven. So they are used routinely by geophysicists even in quite challenging conditions. So you can see the pictures. So they are intended to be used outdoors. They can be transported. They can be used either for long-term measurements. So one of their key features is that they can measure continuously absolute gravity. So that's a strong added value of quantum sensors. Or they can be used for shorter field measurements. We see that there is a growing community of users. So the geophysics community is starting to grasp the added value of this technology, and they're growing and trying to help manufacturers improve the product and so on. And to give a figure of merit and to compare with the other technologies, here we're talking about resolutions which are of the order of 10 to the minus 9G. So that's like the state of the art for these static ground gravimeters. Now, in terms of technology, we're trying to move from static instruments to more portable systems that can be used for gravity mapping, either on the ground. So, for example, the top right picture is what we call a differential quantum gravimeter that can be transported to map small areas. And it has a very high capacity to detect small masses that are buried at shallow distances. So, for example, in the picture here, it was used for archaeology to detect an underground sewage system, which was like a couple of meters below the ground with a couple of meter-like diameter. And this can be detected with really high sensitivity and really short measurements. So that's one direction that we're taking. So moving those sensors around to provide maps, and also trying to put them on more dynamic carriers. And there's been a lot of work, and the state of the art is clearly owned by Onera in France, to go from Earth sensors to seaborne or airborne devices that can measure and map out larger areas. And this is very challenging because you have to take into account the movements of the carrier, which have a huge effect. All the accelerations basically end up being measured as gravity by the sensor. And in that case, so the kind of resolutions you can target is more 10 to the minus 6 to 10 to the minus 9 G. And here again, quantum sensors have proved to provide added performance with respect to their classical counterparts. And so this is the development in terms of where we're heading in terms of instruments intended for end users, but there is also a strong research that's continuing to go on, which is like pushing the field forward. Again, I've selected a couple of items, but it's not exhaustive at all. I think an important point, at least to improve ground sensors for geophysics, is pushing the performance to the limits, so in particular the accuracy. So understanding all the limiting systematic effects so that we can get a better absolute value of gravity. And this is also very important for missions like CARIOQA. There are new ways to manipulate the atoms so that the systems can have much enhanced sensitivity, so they can measure much smaller effects. So this is also being studied in labs, and maybe one day it will be transformed to instruments. And also very interesting, over the past few years, there's been a whole bunch of new techniques and ideas for fundamental physics, for Earth observations, where it's not like single sensors, but networks of sensors that can be either combined over very long distances. So that's called very long baseline atom interferometries, trying to put instruments into networks to kind of have an image, for example, for volcanoes or so on. And also new instruments like using clocks to map out the gravity potential, which is like a complementary kind of measurement with respect to gravimeters. So it's like a quick overview, and I hope it.
Thank you very much. Yeah, thank you very much for this overview. So you said that you can use those gravimeters to give a map of the Earth gravity field from the ground, but then it leads to my question to Christian, which is so how we could use those sensors to support the monitoring of climate change. How does it help to have those gravity maps?
Okay, as it was outlined already in the short movie and by Vincent, gravity sensors can be used to track changes in mass or changes in density. And one of the questions that would go. So, for example, what happens to the glaciers or to the ice in the northern parts of the hemisphere? Where does it go, and how quickly does it vanish, or how quickly do the mass distribution change? And observing these changes can give us insights into how quickly the situation deteriorates, or if the measures that we are taking to slow it down are actually helping. And one thing is, of course, when we're thinking about this whole Earth, this is then more of a global thing. But even on a more local scale, droughts can be a problem. And there are local sensor networks or sensors that can be deployed locally for a short amount of time, could give us additional insight on where the groundwater is going, which is part of this whole getting more insights into the climate change. And another point is then, of course, via tracking this can also help to get better models on what's going on, because whenever we are talking about tracking, whenever we're talking about measuring gravity from Earth or from every kind of mass, this always needs a model to interpret the signals that we actually get.
Yeah, I think that gives us a good answer to this question. Thank you very much. So I think with those three questions, we had a good introduction to the subject, and now I'm going to ask you questions, and you can all answer with your insights on the question. So my first question is how your research in your groups, in your companies or agencies, they contribute to the field of quantum sensors. Well, on ground, because it's a topic today, but how do you contribute on your companies or laboratories?
Okay, maybe I can start. The contribution of our research team is metrology of the sensor, so what Vincent mentioned as something like a continuous effort to understand what are the limits of this technology, what are the limits in the sensitivity, what are the limits in the accuracy. So in my team, my lab, we design and we build and we evaluate the metrological performances of those sensors, trying to understand their limits and pushing their limits pushing the performance to their limits. Yeah, this is what we do at LNE, at LTE, sorry.
And so maybe I can jump in. So, and we come just after that. Basically, it's our role is how we can turn these lab experiments or demonstrators into products that can be used on the field. So of course, some compromise has to be made on the raw performance to make it smaller, more robust, usable by people who don't know about physics. But so I think our, if I was to say our contribution over the past decade, maybe was turning huge lab experiments like exist at LTE into more portable instruments, and hopefully they will continue to get smaller and smaller and more reliable and more user-friendly over the years to come.
Okay, yeah. My role is somewhere in between these two roles that were just defined by Franck and Vincent. So DLR's mission in general is to push things from academia into application. We are not developing products, but our mission is to bridge the gap in TRL between something that is academically researched and that can later then be used by industry. And specifically, the department that I'm heading is working on quantum sensors. So in the field of atom difframetry, be it for measuring accelerations, rotations, or gravimetry. So this whole CARIOQA mission and the general question fits very well into our scope of work. And apart from the space sector that CARIOQA is covering, we have also projects that are developing sensors for terrestrial operation.
Maybe I can add something. I don't want you to say that my experiments are huge. You know, they are just big. And they are not that unfriendly. They are very friendly to quantum physicists. We have all the knobs we can play. Interesting is indeed in those labs experiment, we made them somewhat so that they remain versatile, that we can implement changes, that we have all the control, all the knobs. And this is something different than developing a product where you have basically to make some choices in the design and you have to avoid that the unfriendly user would move the knob that makes that it doesn't work anymore. Okay, so.
And if I may comment a bit, so when going from the lab into the application, then suddenly nasty questions arrive whether the sensor can handle the environment that the sensor is going to be placed in, be it plane, be it in the system in orbit, or be it a car, or whatever the system may go. And suddenly also legal and safety restrictions arise. So this is a whole new area that one then needs to tackle.
Yeah, and talking about user friendliness, basically something that was quite challenging at the beginning is that the users, geophysicists, basically they don't know what an atom is or what a laser is. And so it goes from having knobs to turn into having zero knob to turn, and the instrument has to handle everything by itself. And that's actually quite challenging. And you still have to provide the users sufficient insight on what's going on so that they are confident with the data. So there's kind of a balance that you have to find between giving them access to some like monitoring parameters of the systems, some things that they can tune so that they are confident that they're getting good quality data. And that was also something that was not fully expected at the beginning, but also quite interesting.
Yeah, I think the confidence into the results from the sensors is a quite important part. That it's not just recording something that could be internally generated, but that it is an actually signal that it compares well to the existing instrumentation.
Yeah, thank you very much. I think you've shown us how you bring those apparatus on the ground, on the field, etc. But the main question is, what are the limitations of these instruments? In what's a what is still needed to be improved? What are the next steps for those sensors?
Okay, so again, there are probably many ways to answer. Currently, from our perspectives regarding simple gravimeters, so not looking into next generation instruments, we're at a stage where we have manufactured several of them, probably more than anyone else. And now the challenge is making sure that the sensors that we manufacture all operate at the same level of performance, which is not quite state of the art, but not far from it. And that they can operate at that level of performance over years and years, even in challenging environments, even when they're stored for months without power supply, even when they go in the cold, in the heat, in the dust, and so on. And we have to go from prototypes into something that can be completely reliable so that geophysicists just can trust it and just set it up, press start, and then get some good quality data. And it's not so much into like a science challenge, it's more engineering, but still quite interesting because at that level of performance, every temperature instability, every problem turns into a physics problem because you have to understand how it impacts the measurement in the end.
Yeah, okay. The sensors rely on many, these are relatively complex instruments. So we have many like key subsystems, and to get the best performance, it's important that you are able to master all possible like sources of noise and systematics. So this is something that, I mean, we spent a lot of time studying in detail, and one can actually make that, contribution from the lasers, which are actually the good in this technology. I mean, without the lasers, we would not split the atomic waves, but many of the bad effects that we have actually come from the lasers and the fact that they do not really behave as perfect as they should. And so one spends a lot of time to master those lasers, make them super quiet, and in the end, at the limit, if you have worked well, is the ground vibration of the ground. And one has to realize that this level of performance we get, where we get sensitivities of a few, say, nano-G at 1 second, it requires that we make an effort to shield the experiment from ground vibration, because the vibration noise of the ground is like 3 orders of magnitude larger than this. And it's something that scales also with the scale factor of the instrument. So if you increase the time during which you operate the interferometer, you increase this time between the consecutive pulses, you would say, okay, then I increase my scale factor, I have much larger signal, but then vibration also increase the same way. You cannot distinguish the ground vibration from the acceleration of the atom in free fall, because we do just basically the difference between those two quantities. So you can always turn the instrument by pushing the interrogation time to a regime where vibration noise is the dominant source of what limits the stability of the measurement. Vincent mentioned that okay, there's those gradiometers where you have this. You just basically realize two gravimeters that you put on top of each other, and then they are interrogated by the same laser. So you create the atom interferometer simultaneously on the two gravimeters, and then what you're interested is in the difference between the two measurements. And the vibration noise then is common mode, and it gets suppressed. So this opens also a new avenue for pushing the performances, because in those differential configuration, you can get rid of what is the dominant real killer when you do just single acceleration measurement. And then eventually you can reach limits where it's really the quantum measurement that you realize on the determination of the probability that you detect the atom in each of the two ports of the interferometer. This is a quantum measurement. There is associated to this a noise, which is a quantum shot noise, like what happens with photons. And this in this regime of this differential measurement, this is a limit. But this is not a limit that you cannot beat. And there are also methods to eventually use quantum states that allow to overcome this limit and realize measurements with noise which is below this quantum shot noise. So, and this is something like it's a very active field of research today. Very promising. It has been promising for a long time, so it's still something like difficult. But you need those differential configuration to be able to reach this fundamental limit and then eventually find a way to do better. So there are, okay, the sensors that we have, they already have demonstrated level of performances that make them really appealing for application. They have there's a concrete market, so there's an industrial perspective, but this is not the end of the story, despite the fact that it's like a 30 years old field of research, but it's still very active and there are many routes for improvement.
You're saying that there are no limitations that are not that you cannot overcome with physics, right?
So the typical questions that I usually get when I present these kinds of sensors on conferences or wherever is, what's the size, what's the mass, what's the power budget? And then I typically say, well, this will be difficult to achieve in this volume because we need the laser system, we need the control electronics, we need the physics package. And even if the area where we manipulate the atoms is just like thumbnail, because we can engineer interferometers that are very sensitive on short drop times, we still need the peripherals. And with the peripherals, so with the optics, coils, and how we generate actually and trap the atoms, there's a lot of research ongoing to further shrink down the sensor heads and to further compactify these sensors, because with trade-offs, of course, there's always then the point we can probably only shrink these sensors so far, and at the end we will then arrive at the point where we need to make a trade-off and to design the sensor application specific. And I think this is on the other side from the scientific way. This is one of the other challenges to design the sensors application specific and to get them as small and low weight as possible, and also combining with a low mass, the best way that one person can carry it around, or that it can be launched, that it can be easier launched as a payload for a satellite.
Thank you very much. I don't know if you have questions from the audience.
So first question from the audience. Do you get a better signal if you let the wave packets fall for longer? And if yes, how long would you have them evolve in the measurement, and how long is the cycle time in total, including the preparation of the sample and the measurement?
Okay. So typical experiments on the ground, okay, we are actually limited by the size of the setup because the scale factor is, say, it's a gravimeter, so it's GT square, so it's the drop height. So 10 times more signal requires a 10 times bigger experiment somehow. So then it may be huge. It may become huge if you want to target the largest possible signal. So then to answer the question on what is the cycle time, this depends very much on the implementation. Some people realize relatively small sensors that operate at a high rate. For instance, those which are embarked onto mobiles, platforms like planes and ships. So there you will have more like 100 millisecond cycle time, a few tens of milliseconds for the time of the interferometer. So atom fall over just a couple centimeters or so. And you have a dead time for the preparation and the detection, which amounts to a fraction of the cycle. But on the other side, some people are actually working on like 100-meter tall fall. So then you can have seconds of interrogation, and then this dead time might become very small because the time to prepare the sample could just amount to a very small fraction of the total cycle time. So then you have an efficient duty cycle. You spend most of the time measuring the signal and not preparing the atom. So there is no single answer to this question. It depends very much on the implementation. And another thing is whether you use cold atom or ultra cold atom, whether you use a laser cooled atom sample that you can fabricate very fast, you can have a decent number of atoms enough that this noise I mentioned, which is the fundamental shot noise, is like much smaller than the phase noise of the interferometer, vibration noise also. For that, you just need 1 million of particles, and it takes like tens of milliseconds to capture them and cool them to the proper temperature. And this is what you get if you use this laser cooled sample. But for instance, for the application to space, I mean, one envisions that BEC would be a much better source because we need a much smaller temperature. And then it takes more time. And typically, this will slow down a bit the cycle time, increase the cycle time, because you need, instead of like a few tens of milliseconds to prepare the cloud, you need more like a second or so.
Just really quickly, a BEC maybe for our
Bose-Einstein condensate. But it's based on the technique that are used to prepare the cold atoms. There are many different techniques. Achieving very low temperature in this like pico-Kelvin range of temperature is possible, but it requires complex method that takes comparatively more time than the one that are used, for instance, in the commercial sensors that you realize.
So that's one of the trade-offs that one can take, either using just molasses-cooled atoms, so cooling a less complex cooling scheme, or going down to the BC scale. And for just to give an image, so when the atoms are cooled, this is a cold gas, and molasses-cooled atoms will expand quickly, whereas the delta G collimated BC will stay close together for an extended time. And this makes this lets us exploit this extended free evolution times to the scale of seconds. And in addition, it also enables some of the other advanced techniques that were already mentioned.
Yeah, delta G collimation being another technique to have even colder atoms, let's say. Okay, great. Thank you very much. Do we have another question? Ah, yes.
Okay, so when you think about remote sensing from satellite, you tend to think in terms of imagery, so and spatial resolution. And when you talk about what will be the next requirements for gravity measurements, increasing spatial resolutions, and of course temporal resolution would be one of the goals, the objectives. But you would like to increase the interrogation time to get a higher sensitivity. And you're flying on a platform that is moving at 7 kilometers per second. Therefore, if you integrate, let's say, for 20 seconds, you will move 140 kilometers. How does the increase in sensitivity and the spatial resolution, the meeting point where we would like to have a good enough spatial resolution at a good enough sensitivity that can then be translated into features that you can observe at that scale?
It's a good question and complex somehow. So operating with like interrogation times of a seconds or so, as in the CARIOQA case, indeed leads to a spatial resolution that, when comparing with what one gets with the other mission, is not that different. So it's not that game-changing in terms of spatial resolution. And here, there's a compromise somehow in between the performance and the spatial resolution. But you cannot win both, except if you change the laws of aerodynamics and your satellite flies slower, at a lower velocity. I can extrapolate to a far future in which indeed we will have sensors that would operate in a regime where we are not quantum projection noise limited, that we have actually overcome this limit. And then eventually you can get the same kind of acceleration resolution, but with a shorter time. And then for a given target acceleration sensitivity, then you reduce, improve the spatial resolution. But today, these are methods that need to be demonstrated. So maybe more, one could say, okay, another alternative would be to get a larger number of atoms in the interferometer so that in the end you have less detection noise. But it turns out that it's hard to produce those samples of B, C, delta kicked samples with a larger number, much larger number than what was already done in the labs. One would need something a different principle, something that breaks the limits, and maybe this will come, but there is no real perspective for building, a source that is able to produce billions of atoms at 100 picokelvin temperature. Maybe you have some ideas, I don't know.
I agree that that's going to be tough. On the shorter time scale, I think hybridization should help. So the combination of the atom interferometer, which provides a drift-free signal, and combining this with a conventional or some kind of other signal which tracks the gravity signal at a higher frequency, and then combining these two sensors, this can also help in getting to higher frequency, into the regime where higher frequencies are interesting. And if we're thinking about a ghost type mission, then I would totally agree with your argumentation. If we're thinking about, so a ghost type would be a gradiometer on a single satellite. And if we're thinking about a system with a GRACE-like setup, so that would be 2 satellites in a leader-follower constellation, I'm not sure how the distance of the 2 satellites plays into the spatial resolution there, because this might be at some point also limiting, because you need a certain distance to properly track that. But I'm not too deep into that, but I would expect that there also stems some limitation for the spatial resolution.
And another way of seeing it is ground techniques can also play a role. Because with static instrument or ground-based instrument, you can do mapping at meter-like resolution, of course, over very restricted areas. And then you can have intermediate scales with planes or boats and so on. And so my understanding is that combining measurements from several scales is also a topic that is looked into by geodesists and geophysicists to try and get the best model altogether. And that's why the community is also overlapping between people working on missions like CARIOQA and more local measurements.
Good, thank you very much. We have a question here.
Probably a less complex question, but I was just, I missed the information. I was just wondering, why do you use rubidium, and if it would also work efficiently with another element?
Don't you like rubidium? Rubidium is a very nice and friendly atom,
Because it's pink.
No, I mean this working principle that I mentioned with manipulating quantum states. Basically, any atom would do the job. So you are free to basically choose whatever source of atom, and then comes the complexity that is related to changing atoms. Changing atoms induces that it makes that you need to change the frequency of the lasers. So some atoms are nasty because you need lasers at wavelength where there is no laser, or very sources which are not so high grade with the proper level of stability. But in the community, people are working on atom interferometry with different atoms like cesium, rubidium, all different kinds of alkali atoms, but you can have alkaline earth atoms, other atoms that have actually specific features that make that they somewhat it's still the same kind of interferometry experiment, but with maybe single photon transition. So this I not explain, but the Raman lasers is a double photon transition. So it's transition between two hyperfine states of rubidium. This is where rubidium is nice because you need this hyperfine transition that you have in alkali atoms is key for this two photon process, that you can create the superposition of those two states in their ground state with an optical transition. But in principle, you can do that with a single photon transition, provided that you have an atom where this excited state is long-lived, because when you have created the separation, then you want the atom to stay in the same state when they propagate. So you need eventually long-lived states. So I hope I answered somehow your question. I don't know.
Just to add on the lasers, rubidium, the transition that is interesting is at 780 nanometers. So it's just at the barrier between visible and infrared. And it turns out there are several ways to generate light at that wavelength. But one of the ways that is the most robust is to use lasers that were developed for the telecom industry at 1.5 microns, which are then frequency doubled. So basically, you can convert the frequency of the laser. And these telecom lasers, they've been existing for very long, so they're very mature. There's plenty of components. It's all fibered, so it means that you don't have to align mirrors and so on. And so it's from a technical perspective, it makes rubidium very attractive because we can build lasers that really work great.
I think we. Oh, sorry.
Yeah, and another thing is if you go to different species, then you might require not just one cooling frequency, but different cooling frequencies, which can easily then double the kind of complexity of your laser system, which can be annoying if you're looking out for space weight and power. And another thing, which can be more on the technical side, if you have to use UV lasers, for example, then this can be bad for the optics. And if you're especially thinking about a system that shall last for 3 years or longer, then it's of course bad if the viewports of the vacuum chamber or the other optics go blind.
Another thing, so we need vapors, because we start with a vapor and we cool the atom from the vapor. And to produce a vapor, some atoms, you have to heat them at 1000 degrees. So you need a big oven, so something that you may not want to send into a satellite, because then the swap would be just forget it. Maybe, and then to add to what Vincent said. So Vincent sold basically the technology they sell. We have the lasers with this frequency doubling. But key is that the development of the manipulation of rubidium and cesium was somehow pushed by different factors. One is that you have a vapor without heating, or heating at a very low temperature. Second, one would have super good lasers, semiconductor lasers, directly at 780, 850 nanometer. And actually for rubidium, it's interesting that this 780 nanometer was the transition of the laser that were used in CD and DVD players and printers, okay? So then, for some time, but this time is over now, the industry would produce super robust diode lasers at 780 nanometer that would live for 20 years with no loss of power, moderate power, but they were extremely good sources. And we still have some in the lab. In some of our experiments, we have lasers that we have mounted 20 years ago, and they have the same power as the very first day. Okay, now CD and DVD players are just dying, and this market of producing large-scale production of those semiconductor diode laser somehow disappeared, and there are the knowledge of the production of those is still there somehow, but it's something that you are able to produce a semiconductor and make it a laser, and to really sell a product that lives 20 years without losing a single milliwatt. This is challenging and difficult. So I would like that those sharp diode lasers that we bought 20 years ago would still be there. Now we are obliged to buy telecom laser system based on frequency doubling lasers.
Sorry.
Diode lasers at 780 are still available, but there's still an active field of research.
Okay, thank you very much for your question and for your answer. We have someone on the chat who said, Christian Schubert mentioned briefly quantum sensors that would measure rotations. Is that a different technology and can that be applied to remote sensing?
It's pretty much the same. So when you compare when you think about the scheme that was shown during the short video or that Frank explained, then if you simply add an additional drift velocity to the atoms and not just let them drop them, but you give them a drift velocity in this direction when you apply the lasers from below, then the superposition states enclose an area. And then resembling the Sagnac effect from optics, you are able to track rotations. And yes, this is applicable to remote sensing. However, the developments for gravimeters and radiometers are much more ahead in that direction.
Yeah, rotations actually tend to come as a problem when you're trying to measure very minute accelerations. So we try rather to get rid of them rather than to measure them with the atoms. And maybe another reason is that quantum gravimeters are at the level or better for some application than their classical counterparts. For acceleration sensing in space, atoms are really like the future. For measuring rotations, there are several technologies for gyros, and I'm not going to advertise for any of them here. But basically, it's possible to make extremely good classical gyros that are very compact, very high resolution, very stable on the long term, and so on. And so it's not so clear that there is a benefit from using atoms, at least right now. So it's a field of research. I think many teams, including ours, are looking into that, seeing how we can combine classical and quantum sensors for measuring rotations. But it's not so clear that there would be an added value compared to classical technologies, which is not the case for acceleration.
Somehow I have to agree. Yeah, indeed. So if you look at the literature and you Google, quantum sensors for rotation, you will find that there's still quite some investment and efforts because this quantum technology is also a candidate for building quantum IMUs, quantum inertial measurement units. So can we profit from the long-term stability of the sensors? Can we integrate them into inertial measurement units that would improve positioning with no GNSS after a very long travel time? So there's a strong push to develop accelerometers, and somewhat quantum accelerometers can do and can perform good enough, eventually better than classical accelerometers for navigation, keeping a relatively small form factor. Whereas for gyros, the question is, we can somewhat get the same performance, but with an experiment that is like 1,000 times larger in volume or even more. And there is today there are ways. People are just working on trying to get equivalent performances on much smaller devices, and this would be necessary to really put those quantum sensors and use them for inertial navigation, for instance.
Just to add that it's a thing that is actively looked into right now. Yeah.
Yes, and I saw in the chat there was a question also on those sensors, so gyroscopes and accelerometers. Someone asked if they are already in space or if it's still a project.
So as far as I know, quantum accelerometers are not in space, but there are several demonstrations of cold atom in space. There is a BC experiment on the International Space Station for a few years now that has been doing some science, and I think including some interferometry and clocks. Also, there's been a mission launched a few months ago that features a cold atom clock that is also on an external payload on the ISS. So no quantum sensors in terms of inertial sensors, but a definite interest from the community for cold atoms in space for several reasons, but namely because going to space and increasing the interrogation time has many interests. Acceleration is one of them, but it can be also for fundamental physics, testing like the equivalence principle, testing redshift theories and things like that, and can be accelerometers, clocks, combination of those two, and possibly other things.
I can add on that. So as far as I can recall from literature, there are experiments on the Chinese space stations on rotation sensing. And on the Cold Atom Lab on the International Space Station, there were experiments conducted, so basic experiments to demonstrate that interferometry does work in a spaceborne payload, aiming for acceleration measurements. And one more recent publication demonstrated a differential magnetometer, which basically combines two accelerometers and to then derive a signal from the differential, derive a differential signal from the two accelerometers there. So there is already a lot of work going on in space, but it's not by far not at the level at the technology demonstration level that we're aiming for in CARIOQA. This is more the steps before that.
There's also been some demonstrations on platforms, microgravity platforms, which are not quite space, but intended to demonstrate the technology. So micro zero-G plane, drop towers, sounding rockets, Einstein elevators, and so on. So again, it's a very active field of research, even if it's not been to space because it's expensive, challenging, and so on. But the physics is actively looked at.
Yeah, and each has its merits there because the experiments on the zero-G Airbus and the sounding rocket and the drop towers, these were the experiments that are now paving the way for space, because there we could test a lot of the relevant techniques, and there we could learn a lot for future sensors in space. The thing that's really badly missing there is that it's tough to get statistics because there's only a very limited amount of microgravity time. This will be changed a bit by active drop towers, but this is still not the same as demonstrating something in space that works in space and increases the technology readiness level there.
Yeah, we were talking about vibrations earlier. The best environment would be a satellite, of course, if you want low vibrations. So I think it's a good conclusion for this roundtable. Or we can have a last question, I think. I don't know what time is it. Yeah, we can have a last question if you want. Yes, Pascal?
Yes. It's a very basic question. We talk about ultra cold atoms, but there is no constraint about the temperature of the chamber. It seems strange. No? How could you explain this?
So what is, can you be more specific? I mean, what would you expect?
I would expect some radiation, some infrared radiation inside, and some movement of the atoms.
Okay. Okay. This temperature that the atoms are is actually not really a temperature of a thermal equilibrium with the atoms with its environment. Indeed, because the chamber is at least on the ground is at room temperature. The atoms are there, so they are very isolated from the environment because they are like kept by the lasers. But indeed, there is an effect of the radiation by the chamber, and people have actually measured the acceleration shift related to the black body radiation of the surrounding masses. So this is something that one has to consider as a systematic in like CARIOQA, for instance, that the proximity of the chip and the temperature of the chip, there's a question whether there's a bias related to this black body. It's a gradient somehow, so even you get a force and you get an acceleration. So there's an effect. But it's not an effect that eats up the atoms and make them, move around like hell. They are very cold, but it's more like they see a gradient, so it's like a parasitic force that in the measurement is like interpreted as an acceleration.
So it's one of the many challenges that we have to face when we want to put those accelerometers on a satellite. And so this is the aim of the mission CARIOQA. And this is the end of this first webinar. So I hope everyone enjoyed this time of exchange, this time of discussions. Thank you very much to our panelists for their answers and for their very interesting insights on the topic. It's been really clear, really interesting to listen to. So thank you very much. Thank you very much for attending here at CNES, but also online. I would like to thank the people who helped us organizing this event. And a special thanks to Dimitra, who was one of the organizers of this event, and I think she's online with us, but she was not able to be here with us tonight. So thank you very much, and I think we can give them a last big round of applause.